In this video I am going to shoot an electron towards a bunch of different potential wells and barriers using computer simulations. And not because it's just a lot of fun, but also to learn a lot of stuff about quantum tunneling. And to answer some interesting questions, like does the electron always tunnel? Or is there a potential that is completely transparent? We'll also look at the Fourier space and its time evolution, and also the real and complex part of the wave function. And is there a good intuition to have regarding tunneling effect in quantum mechanics? Or is it just a combination of many effects and it's very difficult to make sense of it? Okay, so according to quantum mechanics, an electron looks something like this: a lump of probability. In principle, it can be any smooth function, but Gaussians are used to model some realistic localized particles like electrons. When you do computer simulations, you usually want to work with nice numbers and set the h bar and mass equal to 1. But if you then rescale the coordinates, which is very painful, you can get more familiar units. So if you put a mass of an electron, then you get the scale in nanometers and time in femtoseconds, which is 10 to the minus 15 seconds if you were wondering. So what happens if you let this configuration evolve according to Schrödinger equation? Well, we shouldn't expect anything interesting since it's single particle in empty space. So if we do that, we'll find out that it just starts to spread. First, we want to answer why, but also what happens if we start with more localized peak. Let's compare these two initial peaks, one sharper and one more spread out. If we start the evolution, the sharper peak spread much faster and even overcoming the wider one. But that is weird. At certain time, these two are of the same width. So why the blue one continues to spread out faster? So just a single particle in empty space and yet so many questions. We can even make it more pronounced, and what we see that the more localized particle is at the start of the simulation, the faster it dislocalizes itself. But it makes sense. And why? Because of the Heisenberg uncertainty relations. This is the wave function in the so-called position representation. But by the Fourier transform, you can also look how the wave function looks like in momentum representation. And this is also a Gaussian. The standard deviation of this Gaussian in position space times the standard deviation in momentum space must be always larger or equal to some small value. So by having very sharp peak in position space, you must have very wide peak in momentum space and vice versa. And this should probably give you a clue how to solve this problem. So this Gaussian can be interpreted as being made of many pieces, all having different momenta. And then obviously, if there is more spread in momenta, then these pieces separate much faster. It makes sense, but it still doesn't explain why this sharper peak overcomes this wider one. Shouldn't be the uncertainty in momentum here be the same when they are on top of each other? What happens to the momentum space wave function if we evolve it in time? So let's try it. Here I have position representation and below the momentum representation of the wave function. And now I evolve it in time according to the Schrödinger equation. So apparently, a momentum wave function doesn't care about the time evolution. But now it makes sense. The Heisenberg uncertainty relations are only restriction from the bottom. But overall uncertainty can be anything. So if you start sharp, you set initial uncertainty in momentum space that will remain the same forever. And therefore the peak will spread faster forever. So that would be one question answered. But now, how do we make this Gaussian peak move? And in fact, it's quite easy. You just multiply it by a complex exponential term, where this k is the amount by which the mean momentum is shifted. So the intuition is very simple. By multiplying the Gaussian by the complex exponential term, I will just add a constant to all the pieces of the Gaussian. And therefore, if I evolve it, it will be spreading and moving at the same time. Another thing to note is that what I am depicting on the graph is the absolute value squared of the wave function, which is the probability density. And therefore the Gaussian peak with added momenta looks exactly the same as the Gaussian without added momenta. The difference is in their complex part of the wave function. In quantum mechanics, the probability current is defined like this, and therefore if you only have a real valued function, there is no probability current, because these two parts just cancel out. But if you develop the zero momentum Gaussian in time, the complex part will develop, because the probability starts to flow. Okay, that's a good thing to know, but let's start doing some more fun stuff. I wanna shoot Gaussian towards a potential barrier. So I make a graph with some barrier at the center, with some width and height. Its height corresponds to the potential energy, and therefore classically particles with less kinetic energy would not be allowed to cross the barrier, but particles with higher energy would just slow down for a while, and then speed up back again. Now I model a Gaussian wave packet like this, with such normalization that the peak corresponds to the mean kinetic energy of the electron. But I will also include this yellow line so that you can clearly see whether the mean kinetic energy is above or below the barrier. In this scenario, I have the potential barrier with a height of 5 volts, and I gave the Gaussian mean kinetic energy of 4 electron volts, and therefore below the barrier. If I will evolve it in time, this is what happens. Some of the probability will go through the barrier, and some is reflected back. So in the end state, we have two Gaussians. But, and this is important, we don't have two electrons. This end state wave function still describes only a single electron, but there is non-zero probability to detect it before and also beyond the barrier. And if you let the time flow, one part of the wave function can be in Andromeda galaxy and the other in some other galaxy, and it is still a single electron. If you measure it somewhere, then the wave function collapses and becomes a single peak back again. The event of detection, the energy transfer between the electron field and your measuring device, is what we call electron. But how can the wave function in the Andromeda galaxy know it was detected? This is called the measurement problem, and it is one of the open questions in all of physics. But anyway, I thought that this is gonna be just a bunch of fun animations to make. But I gained a lot more intuition than I expected, again. So just out of curiosity, I also looked on how the Fourier space wave function evolved in time. And this is it. We see that originally we have a single peak shifted by some value that corresponds to the energy of 4 electron volts. But right away here, from the initial configuration, you can see something. If you denote the momenta that corresponds to 5 electron volts, which is energy needed to cross the barrier, you would get this. So you could sort of expect that everything to the left from this line will get reflected, and everything to the right will be transmitted. So let's evolve it now, and this is what happens. So as expected, the initial peak splits into two. This left one corresponds to the reflected wave as it has negative momenta, and this small right one is transmitted. And notice one thing, this right one has quite higher mean energy than the potential barrier. So it seems like our intuition was correct. The parts of the wave function with higher momenta crossed the barrier, and the ones with less were reflected. And don't think of this barrier as a real barrier that should slow everything down. No. Classically, it should slow down a ball only in this region, as it crosses the first jump, but then it speeds up back as it descends from the second slope. So classically, anything that crosses should have the same momentum as before the ball. Okay, so transmitted wave makes almost sense, because even though it's true that on average energy is now well above the energy threshold of the barrier, you can still detect electron to have lower energy than the barrier, which classically shouldn't be ever happening. Moreover, if you look at the left peak, you see that the peak was reduced here in the higher energy part, which again kinda makes sense since only the slow parts were reflected. but there is also non-zero chance to detect electron with energy higher than the barrier. So that will mean that electron got reflected even though it had enough energy to pass through. Additionally, there is a small additional peak, which I'm going to explain later. But it's very interesting to ask why it's there. So it seems like quantum mechanics is quite intuitive, but only on average. But if you think about individual measurement, it can produce results that are impossible to explain classically. From this knowledge, I would expect that this intuition is gonna be even better if I make the potential wider. So let's try it. Now I evolve this Gaussian against much wider well, and you can see that some of the wave is going through again, but there is also this part of the wave that is kinda trapped inside the barrier, causing interferences. And that's why we see this shakiness. But let's look at the Fourier space again. You might notice that this shakiness is even more pronounced, but also you can see that the transmitted wave has energy spectrum almost entirely above the potential barrier. And you can also see the steeper decline around the green line on the left. But still, here are some areas with quite high probability of detection that shouldn't exist classically. Again, I will explain that later. Okay, so now I thought that width of the Gaussian corresponds to the uncertainty in momentum. And as I already showed you, making it very wide makes the uncertainty in momentum very small. So let's try to make the width of the initial Gaussian large, but the average energy is still below the barrier. So we'll use the original configuration of electron with 4 electron volts and the barrier with 5 electron volts. That has the same width. I just had to make the initial separation larger. But such a white electron does localize itself very slowly, so it is not that big of a deal. But after the collision, you barely see anything going through the barrier. So it seems like the tunneling is disappearing with more localization in momenta. We can check everything all over again, also in the Fourier space. You can see that in momentum representation, the electron has sharply localized momenta as the start. And when we run the animation, we see that most of this probability just changed the sign, as the momentum of the reflected wave is now in the other direction. But just a very small peak here of the transmitted wave. Moreover, the secondary peak is gone. So it really seems like this tunneling effect is just due to Heisenberg uncertainty relations in momentum space. But be careful with this intuition, as I will show you later in the animations. Just for fun, let's try giving the electron 5 electron volts, so it has the mean energy the same as the potential barrier, and leave the width unchanged. So this is our configuration now. I would expect 50-50 split. Half of the wave is gonna be transmitted, and half of the wave is gonna be reflected. So what happens? And in the end, transmitted part is much smaller than the reflected part. But how can this be the case if in the Fourier space the Gaussian lies exactly at the threshold and you measure 50% of a time electron with higher energy and 50% with lower energy? So there must be something outside our intuition. It is good enough, but it is not the full picture. Okay, let's try to build a potential that is completely transparent. The obvious choice is having no potential whatsoever, right? But that's boring. But let's make it negative. Now we have a potential well instead of barrier. So inside the well, the kinetic energy should be increased and not lost, and therefore we shouldn't see any reflections, right? So let's play the animation. So as expected, the wave came through, but there seems to be something also going back. There is still some wave reflected from the boundary. And we can also see it more clearly in the Fourier space, and there is a chance of detecting the electron with negative momenta. But let's make something completely different. Let's make not potential well, but a step. So this is classically almost like a cliff. Anything that goes in this region will just gain kinetic energy and keep it forever. Because in the previous case, it could be this steep climb in the potential that was responsible for the reflection. But in this one, there is no such thing anymore. So if you play the animation, there is still something coming out. But why? Imagine you have a classical ball and a cliff, and this ball gets reflected from the cliff. Physics like this would save a lot of lives, right? But it doesn't make any sense. And that is not all. Let's make this step more shallow and play the animation. So it seems like almost the entire wave went through. So the more shallow step, the less wave is gonna be reflected. Does that mean that if I make the step very large, then a lot of wave is gonna be reflected? Okay, here I have a step of negative 20 volts. Let's play the animation. And it seems that it's correct. Quite a large chunk of wave is reflected. So the probability that your ball is gonna be reflected off of a cliff is larger if the cliff is very deep, apparently. So you see, our initial intuition goes completely through the window now. But at least now we can explain this secondary peak here. Because when you shoot a Gaussian to a barrier like this, part of the wave gets reflected on this first wall, which is this big peak here. But a wave with high average momentum will get into this part of the potential, and a part of that wave gets reflected here. And that is why you see the secondary peak with very high average momentum. The fact that our original intuition is wrong is further strengthened by the fact that instead of Gaussians, you can use plane waves with definite momenta, and you will have non-zero probability of detecting the electron behind the barrier even though its kinetic energy is lower than the barrier. So question: is there a non-zero potential that is completely transparent? And when you work with step functions as your potentials, then obviously no. But if you use some smooth potentials, then that's completely different story. But first, let's try a Gaussian barrier with the same height as the kinetic energy of the wave bucket. So we have this configuration and we run the simulation. And suddenly the 50-50 rule works. These peaks in the Fourier space are almost identical. So the discontinuity in derivatives in step potentials somehow causes more reflections. And it is not just numerical artifact. This is something you can also find out analytically with plane waves. Okay, so does this mean that if I revert the Gaussian into negative values, I will get fully transparent potential and the physics will be saved? So here I tried this configuration, and when I ran the animation, then in fact it seems like the reflections completely disappeared. You can mainly see it in a Fourier space that there is only a single peak. I tried to zoom in, wondering whether I could find some minor reflections, but it doesn't seem to be the case. So is it the case that the Gaussian well is always fully reflectionless? So this is what I tried. I made the potential a lot thinner, but quite deep, and gave the electron a lot lower kinetic energy so that it has enough time to interact with the potential. I also made it a lot wider at the start, which might or might not help, and ran the simulation. And on the simulation, it doesn't seem to be any reflections. But when you look at the Fourier space, there is a small peak here. At this time, having just a visual confirmation whether there are some reflections or not is starting to be not good enough, and it's better to quantify it properly. So what I did is simple. I just integrated this left and right part of the Fourier space separately and compared them. And in this case, there is around 1.7% of the original wave reflected. So the Gaussian is not fully transparent in general either. So the question remains, is there something better? And in fact, there is something not just better, but something perfect. It's called post-stellar potential, and this is it. And if this lambda is an integer, this potential should be fully transparent. So I want to test it numerically, and I want it to have the same depth and width as the Gaussian potential. So if I choose this lambda to be 4, then this gives me the depth of 6, which is the same as original Gaussian. I also choose the w to be 1, so it has roughly the same shape. If I run the animation, I suddenly don't see anything in the Fourier space. But what do numbers say? If I calculate the integrals, I will find out that there is some reflection, but in the order of 10 to the minus 10%, which is something you would expect in numerical result. But it is known analytically that this potential is fully transparent for integer lambdas. By making the initial separation larger, increasing the grid size and resolution, making the evolution longer, I managed to bring it down by 3 orders of magnitude. And I could bring this error even lower, so it seems like whenever I make the animation more clear and precise, this number converges to 0. In fact, not to 0, but to the 10 to the minus 28, which is the outgoing part of the wave function we have from the start to momentum uncertainty. I also promised you to answer the question whether the electrons always tunnel. But I already showed you that the best reflectors are the step functions. But there was always some tunneling present. So there is no finite potential that will be fully reflective. So really the only way is to make the potential barrier as large as possible to maximize reflections. So there is no way around tunneling, and it's a limiting factor in some nanotechnologies like semiconductors. My plan was to show a lot more, like placing a Gaussian inside a bell or atomic nucleus potential, but sadly I don't make videos so long. But I will be playing with this stuff, and if I find something interesting, I might post it on the Patreon for all of you who kindly support me there. And who knows, maybe there will be another video about it, if I find a lot more interesting stuff. So, thank you for watching, and I see you next time.